Right now, as you listen to this, our sun is lying to us. 7 active regions dot its face like dark wounds on a burning god, and the forecasters are calling conditions quiet to unsettled. Quiet. Think about that word for a moment. We use it to describe libraries and sleeping children and empty houses at midnight. But when space weather scientists use the word quiet to describe a star that just hurled a coronal mass ejection at our planet on New Year's Day, a star whose magnetic field is twisted into configurations that could erupt at any moment, well, that is a very specific kind of quiet. That is the quiet of a coiled spring, the quiet of a held breath, the quiet that comes right before everything changes. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. The quiet before the storm, AR4325 and the sun's deceptive calm. Let us begin with what is happening on the sun right now, on the 6th of January 2026. The Earth-facing solar disk displays 7 numbered active regions, and that number alone should tell you something. During the deep solar minimum just a few years ago, we would go weeks, sometimes months, without a single sunspot. Now, we have 7 distinct regions of intense magnetic activity, each one a potential source of solar flares and coronal mass ejections. But the region that has captured the attention of solar physicists around the world is designated AR4325. AR4325 is classified as beta-gamma, which in the arcane language of solar observation means its magnetic field configuration contains both positive and negative polarities in a complex intermingled arrangement. This is not the simple dipole you might remember from high school physics, with neat north and south poles on opposite ends. No, this is something far more volatile. Imagine taking 2 powerful bar magnets and forcing them together in ways they do not want to go, twisting them, compressing them, until the field lines themselves begin to writhe and reconnect. That is what is happening in AR4325 right now, and it is the largest active region currently visible on the solar disk. The region has been firing off C-class flares like a restless giant turning in its sleep. 14 C-class flares in the last reporting period alone, with AR4325 responsible for a significant portion of that activity. Now, C-class flares are what we call common flares, the background noise of an active sun. They are the solar equivalent of clearing your throat, not a full shout. But here is what makes the current situation so interesting. The magnetic complexity of AR4325 combined with the activity from AR4333 and AR4334 suggests that the sun is loading a spring that could release in a much more dramatic fashion. NOAA and the Solar Influences Data Analysis Center both highlight what they call a relatively high probability for M-class events over the next 3 days. M-class flares are moderate eruptions, 10 times more powerful than C-class events, and they can cause brief radio blackouts on the sunlit side of Earth. But here is where we get into speculative territory, the kind of possibility that keeps space weather forecasters awake at night. There is also a slight chance for an X-class event. Think about that for a moment. X-class flares are the titans of solar eruptions. The strongest Earth-facing flare of the current solar cycle was an X 9.0 event that erupted on October 3, 2024. When X-class flares are directed at Earth, they can disrupt high-frequency radio communications for hours, damage satellites, and if accompanied by a powerful coronal mass ejection, trigger geomagnetic storms that threaten power grids across entire continents. And right now, the configuration of AR4325 means that such an event, while not expected, is not impossible. What makes this moment particularly fascinating is the context. We are now in what solar physicists call the declining phase of solar cycle 25. The smooth sunspot number peaked in October of 2024 at approximately 161, and since then we have been on the downward slope of the 11-year cycle. Conventional wisdom would suggest that the danger is passing, that the sun is settling into a quieter phase. But history teaches us a very different lesson. Consider solar cycle 23, which peaked in 2001. That cycle produced 10 flares exceeding the X10 class level, but here is the remarkable thing. 4 of those extreme events occurred in 2003, 2 more in 2005 and 1 in 2006, all years after the official solar maximum. The Halloween storms of 2003 struck more than 2 years after the cycle peaked, and they remain some of the most powerful solar events in the modern era of observation. The largest of those flares was estimated at X40 class, so powerful it literally overwhelmed the sensors trying to measure it. Solar Cycle 24 tells a similar story. That cycle peaked in 2014, but the two largest flares, an X13.3 and an X11.88, both erupted in September of 2017, more than 3 years after solar maximum. The declining phase of a solar cycle is not a time of diminishing danger. It is often when the sun delivers its most devastating blows. So when forecasters describe current conditions as quiet to unsettled, understand what that really means. It means we're in a lull between potential storms. It means the coronal mass ejection that brushed past Earth on January 4th, the one launched on New Year's Day, only disturbed our magnetic field to quiet levels because the interplanetary magnetic field happened to be oriented in a relatively benign direction. The southward component of that field, the Bez value that determines how much solar energy couples into our magnetosphere, only dipped to about -7 nanotesla for a brief period. Had it been stronger, had it been more persistent, had the magnetic field turned more decisively southward, we would be telling a very different story right now. The solar wind environment over the past few days has remained, as forecasters put it, only slightly disturbed. Wind speeds have been hovering around 450 km per second, rising modestly toward 500 km per second as the CME influence became apparent. For context, the solar wind typically travels at around 400 km per second during quiet times. During major geomagnetic storms, that speed can exceed 1,000 km per second, and in extreme events like the Carrington Event of 1859, speeds may have approached 2,000 km per second or more, but the current calm is deceptive in another way, and this brings us to something that researchers announced just hours ago, something that fundamentally changes our understanding of how active solar regions behave. Scientists using the Solar Orbiter spacecraft have just revealed that they observed the most active solar region of the past 2 decades for a record-breaking 94 consecutive days, tracking it from birth through maturity to decay. The region was NOAA 13664, the very same sunspot complex that triggered the most intense geomagnetic storm since 2003, the G5 extreme storm that struck Earth in May of 2024. This is unprecedented. You see, the sun rotates on its axis once every 28 days, which means any given active region is only visible from Earth for about 2 weeks, before it disappears around the far side of the sun. We lose sight of these magnetic crucibles precisely when they might be doing their most dangerous work. But Solar Orbiter, launched by the European Space Agency in 2020, follows an elliptical path around the sun that allows it to observe regions we cannot see from Earth. By combining Solar Orbiter data with observations from NASA Solar Dynamics Observatory, which monitors the Earth-facing side, researchers were able to track NOAA 13664 almost continuously for 94 days, covering 3 complete solar rotations. What they discovered is both beautiful and terrifying. They watched the active region form on April 16, 2024, on the far side of the sun, a place we could not observe from Earth at all. They tracked it as its magnetic field grew more complex over multiple rotations, each passage adding new layers of twisted field lines and stored energy, and they observed the formation of an intertwined magnetic structure immediately before the sun released the strongest solar flare in over 20 years. Ioannis Kontogiannis, a solar physicist at ETH Zurich who led the study, called it a milestone in solar physics, and he is right. For the first time, we have watched a superactive region through its entire life cycle, from birth to death. We have seen how these magnetic monsters develop, how they store energy over weeks and months, how they finally release that energy in catastrophic eruptions. This is not just academic knowledge. This is information that could one day help us predict when the next Carrington-class event will occur, giving humanity precious hours or days to prepare. But here is the uncomfortable truth that emerges from this research. The quiet we are experiencing right now is temporary. The active regions on the Sun today, AR4325 with its beta-gamma configuration, AR4334 which just produced the strongest flare of the current period at C3.0, these are the descendants of the same solar dynamo that created NOAA 13664. They are governed by the same physics, driven by the same 11-year cycle, capable of the same extreme behavior. And while the declining phase means we will see fewer active regions on average, the ones that do appear can still produce events that rival or exceed anything we witnessed during solar maximum. The geomagnetic forecast for the coming days calls for mostly quiet conditions as the effects of the New Year's Day CME continue to fade. By tomorrow, January 7th, predominantly quiet conditions should prevail. Auroras will remain confined mainly to the auroral oval, visible across Iceland, northern Scandinavia and northern Canada. For most of the world, the sun will simply rise and set as it always has, giving no outward sign of the magnetic complexity seething beneath its photosphere. But that is precisely what makes this moment so important to understand. The sun does not announce its intentions. Active region 4325 is not sending us warnings in a language we can easily read. It is simply accumulating magnetic energy, tangling its field lines, building toward a configuration that will eventually become unstable. When that instability arrives, it will happen in minutes. The released energy will travel toward us at the speed of light, arriving before we even know it has been launched. And if a coronal mass ejection follows, if the magnetic field embedded in that plasma cloud is oriented just wrong, if it arrives when our own magnetic field is weakened by other factors, then the quiet we enjoy today will seem like a distant memory. This is not fear-mongering. This is physics. This is the reality of living in the extended atmosphere of an active star. And understanding this reality, respecting it, preparing for it, is one of the most important things our technological civilization can do. The sun has been quiet today, but the spring is still coiled, the breath is still held, and somewhere in the twisted magnetic architecture of AR 4325, energy continues to build. Solar Orbiter's 94-day revelation, tracking the beast that shook Earth, and that energy building in active regions like AR 4325 connects us to something extraordinary that scientists revealed just yesterday. For the first time in the history of solar observation, researchers have tracked a single active region through its complete life cycle, from the moment magnetic flux first broke through the solar surface to the final decay of its tangled field lines. 94 days of continuous observation, 3 complete rotations around the sun, and at the center of this unprecedented study was the very region responsible for the most powerful geomagnetic storm to strike our planet in more than 2 decades. NOAA 13664. If you followed space weather at all during 2024, you know this designation. This was the sunspot complex that announced itself to the world on May 10th of that year, when Earth experienced a G5 extreme geomagnetic storm, the first event to reach that classification since the Halloween storms of 2003. Aurora Borealis danced across skies as far south as Puerto Rico. GPS systems faltered. Satellite operators watched helplessly as atmospheric drag increased by up to an order of magnitude in low Earth orbit. Modern digital agriculture ground to a halt as the precision signals that guide autonomous tractors scattered into uselessness. But until yesterday, we only knew part of the story. We knew what NOAA 13664 did when it was facing Earth. We knew the damage it caused, the beauty it created, the systems it disrupted. What we did not know was how it became what it was. Where did this monster come from? How did it grow? What exactly happened in those twisted magnetic field lines that allowed them to store such catastrophic amounts of energy? Now we know. And the answer has profound implications for everything we thought we understood about solar activity and our ability to predict it. The study, published in Astronomy and Astrophysics and led by Ioannis Kontogiannis of ETH Zurich and the Istituto Ricerche Solari Aldo Echele da Co in Locarno, represents a collaboration that spans institutions and continents. The researchers combined data from 2 spacecraft that observed the Sun from completely different vantage points. NASA's Solar Dynamics Observatory sits at the L1 Lagrange point between Earth and the Sun, providing continuous monitoring of the solar hemisphere that faces our planet. But the Solar Orbiter, launched by the European Space Agency in February of 2020, follows an elliptical orbit that carries it around the Sun allowing it to observe regions that are completely hidden from Earth-based instruments. Think about what this means. The Sun rotates once every 28 days. Any feature on its surface spends roughly half that time facing away from Earth, invisible to our ground-based telescopes and near-Earth satellites. For all of recorded history, we have been trying to understand solar activity while missing half the picture. It would be like trying to study a person's behavior while only being able to observe them when they face a single direction. You might learn something, but you would miss crucial context about how they move, how they change, what they do when they think no one is watching. Solar Orbiter changed that equation, and for NOAA 13664 the timing was perfect. The active region was born on April 16, 2024 on the far side of the Sun. From Earth, we had no idea it existed. But Solar Orbiter was watching. The spacecraft observed magnetic flux emerging through the photosphere, rising from the churning convective layers below the visible surface. Over the following days, the researchers tracked the region as it grew, as smaller magnetic elements merged with larger ones, as the overall magnetic configuration became increasingly complex. Here is something crucial to understand about solar active regions. They are not static structures. They are dynamic systems constantly evolving under the influence of differential rotation, convective motions, and the emergence of new magnetic flux from below. The Sun's equator rotates faster than its poles, completing one rotation in about 25 days, while the polar regions take closer to 33 days. This differential rotation stretches and twists magnetic field lines, building stress into the system, like winding a rubber band tighter and tighter. As NOAA 13664 rotated from the far side to the near side of the Sun in early May, Earth-based observers finally got their first look at what Solar Orbiter had been tracking for weeks. What they saw was alarming. The region had developed into one of the largest sunspot complexes in years, spanning an area that could swallow dozens of Earths. Its magnetic classification had evolved to Beta Gamma Delta, the most complex and unstable configuration possible. The delta designation indicates that opposite polarity umbrae, the darkest cause of sunspots, share a common penumbra, forced into unnaturally close proximity. This is a recipe for magnetic reconnection, for the sudden release of stored energy that we call solar flares. Between May 3rd and May 9th, NASA's Solar Dynamics Observatory observed 82 notable solar flares from just two active regions, AR 13663 and AR 13664. 9 of those flares reached X-class intensity. This was not normal solar behavior, even for a cycle approaching its maximum. This was a sun in a state of magnetic crisis, releasing energy in repeated explosions as it struggled to find equilibrium. But the crucial insight from the new study is what happened before those flares. The researchers observed the formation of what they describe as an intertwined magnetic structure in the days leading up to the most powerful eruptions. Multiple magnetic flux systems, each carrying billions of amperes of electric current, wrapped around each other in configurations that resembled twisted ropes. These structures, known as flux ropes, are the bullets in the gun of solar eruptions. When they become unstable, when the forces holding them in place can no longer contain the magnetic pressure within them, they erupt outward in coronal mass ejections that can reach Earth in as little as 15 to 18 hours. The strongest solar flare of the past 20 years erupted from NOAA 13664 while it was on the far side of the Sun, invisible to Earth-based observers. Think about that for a moment. The most powerful explosion from this region happened when we were not even looking, when our planet was shielded from its effects by the bulk of the Sun itself. Had that flare occurred 2 weeks earlier or 2 weeks later, when the region was facing Earth, the consequences could have been far more severe than the May 10th storm. This is the terrifying randomness of solar activity. The difference between a near miss and a civilization-threatening event can come down to the timing of the Sun's rotation, the orientation of magnetic fields we cannot predict, the chance alignment of plasma clouds and planetary positions. We were lucky in May of 2024. The extreme storm we experienced was powerful, but it was not the worst that NOAA 13664 had to offer. Louise Harrer, professor at ETH Zurich and director of the Davos Physical Meteorological Observatory, put it starkly in the announcement of the new findings. Even railway signals can be affected by these events, she said. Signals can switch from red to green, or vice versa. That is really scary. and she is right. We have built a civilization that depends on precise electromagnetic signals for everything from navigation to communication to the safe operation of transportation networks. Solar storms do not care about our dependencies. They simply release energy according to the physics of magnetic reconnection, and our infrastructure either survives or it does not. The May 2024 storm particularly devastated modern digital agriculture. Farmers who had come to rely on centimetre precision GPS guidance for planting found their systems useless. Working days were lost. Crops failed in some areas because the narrow planting windows of spring could not wait for the geomagnetic field to settle. The economic losses, while still being calculated, are significant. And this was from a storm that, historically speaking, was not even particularly extreme. What makes the 94-day observation so valuable is the insight it provides into the development timeline of superactive regions. The researchers watched NOAA 13664 go through multiple phases, each rotation around the Sun bringing new evolution, new complexity, new stored energy. They documented how magnetic structures that were relatively simple at first became increasingly tangled over time, how energy accumulated in the corona above the active region like water building behind a dam. This kind of longitudinal observation was simply impossible before Solar Orbiter. We could see active regions when they faced Earth, lose them for 2 weeks as they rotated to the far side, then pick them up again when they returned. But the continuity was broken. We could not know what happened during those hidden weeks, could not track the evolution that set the stage for the eruptions we eventually observed. Now we can. And the implications extend far beyond academic understanding. If we can characterize how active regions develop over their full life cycles, if we can identify the signatures that precede extreme events, we may eventually be able to predict which regions will produce civilization-threatening storms before they actually erupt. That is not a capability we have today. Current space. Weather forecasting relies heavily on observing what is already happening, then projecting how those current conditions will evolve over hours or days. But true prediction, the ability to say that a particular region will produce an extreme event before it actually does, remains beyond our reach. The 94-day study of NOAA 13664 is a step toward that goal. By watching the region from birth to death, by documenting every phase of its evolution, researchers now have a template they can compare against future active regions. When the next potential super-region emerges, Solar Orbiter and its partner spacecraft will be watching, and the patterns observed in 13664 may help forecasters recognize danger signs earlier, giving humanity more time to prepare. But we should be clear about the limitations. One case study, no matter how detailed, does not give us predictive power. Solar active regions are not identical. Each one develops in its own way, influenced by local conditions in the solar convection zone, by the residual magnetic fields from previous cycles, by the chaotic dynamics of a star that contains 99.8% of all the mass in our solar system. The Sun is not a machine that follows predictable patterns. It is a nuclear furnace wrapped in churning plasma, governed by physics we understand but cannot fully model. What we can say with confidence is this: the quiet conditions we are experiencing right now, the C-class flares and modest geomagnetic activity of early January 2026, are temporary states in a system that remains capable of extreme behavior. Somewhere on the Sun, perhaps in active region AR 4325 that currently dominates the Earth-facing disk, magnetic flux is rising from the interior. Field lines are twisting, energy is accumulating. The next NOAA 13664 may already be forming, growing in complexity with each passing day, building toward an eruption that could make the May 2024 storm look minor by comparison. We are watching now in ways we never could before, but watching is not the same as controlling, and as we transition deeper into the declining phase of solar cycle 25, history tells us that the greatest dangers may still lie ahead. The polar field anomaly: why the Sun's northern hemisphere is collapsing. Speaking of dangers that lie ahead, we need to talk about something that solar physicists have been quietly alarmed about for weeks now. Something that does not make headlines because it is too subtle for sensational news coverage, too technical for casual observers, too slow-moving for a world addicted to immediate crises. But within the community of researchers who study our star, This developing situation has sparked what can only be described as genuine concern. The Sun's polar magnetic fields are behaving in ways we have not seen in at least 5 solar cycles, and the implications could reshape our understanding of what comes next. Let me explain what polar fields are and why they matter, because this is one of those pieces of solar physics that sounds arcane, but actually governs everything we care about regarding space weather. The Sun, like Earth, has a magnetic field, but unlike our planet's relatively stable dipole, the solar magnetic field is in constant flux, literally rebuilding itself every 11 years as part of the sunspot cycle. At solar minimum, when sunspots are rare, the Sun's magnetic field is relatively simple, dominated by a dipole configuration with opposite polarities at the north and south poles. But as the cycle progresses, as active regions emerge and sunspots multiply, those polar fields weaken and eventually reverse polarity entirely. The solar maximum is marked by this polarity reversal, this moment when the magnetic north and south of our star flip places. Here is why this matters. The strength of the polar field at the end of one solar cycle is the best predictor we have for the strength of the next cycle. The polar fields act as a seed, their magnetic flux being transported and amplified by the solar dynamo to produce the active regions and sunspots of the following cycle. A strong polar field at solar minimum tends to produce a strong subsequent cycle, with lots of sunspots and high solar activity. A weak polar field tends to produce a weak cycle, and right now the Sun's polar fields are exhibiting something deeply unusual. A study published just weeks ago, in December of 2025, by researchers led by Ruihui Wang, presents predictions for the evolution of solar polar fields from October 2025 through October 2026. Their findings are striking. The southern polar field is expected to strengthen gradually over this period, which is normal behavior for a solar cycle entering its declining phase. But the northern polar field is predicted to decline sharply until approximately March of 2026, driven by what the researchers describe as active regions with abnormal polarity. Think about that phrase for a moment. Abnormal polarity. In the language of solar physics, this refers to active regions where the leading and following magnetic polarities are reversed compared to what Hale's law predicts for their hemisphere and cycle. These rogue regions do not contribute to building the new polar field. Instead, they work against it, their transported flux cancelling the field that should be accumulating at the poles. By March of 2026, the northern polar field is expected to become exceptionally weak. The researchers compared their predictions with data from the past 5 solar cycles and found that the mean polar field of cycle 25 is the weakest at a similar phase across all of them. This is not just below average, this is historically anomalous. This is the Sun doing something we have not observed in the modern era of precision, solar monitoring. What does this mean for us? The immediate implications centre on cycle 26, the next solar cycle that is expected to begin sometime between 2029 and 2032. The strength of the polar fields at the minimum between cycles is our best predictor for the amplitude of the upcoming cycle. If the polar fields are exceptionally weak at the cycle 25-26 minimum, then cycle 26 may be correspondingly subdued. We could be looking at an extended period of reduced solar activity, potentially resembling the conditions of the early 20th century, or even, in extreme scenarios, approaching the quiet conditions of the Maunder minimum that coincided with the Little Ice Age. But there is another possibility, one that the researchers themselves acknowledge. Polar fields can strengthen rapidly during the declining phase of a solar cycle. The flux from active regions takes time to be transported to the poles by meridional flow, the north-south circulation patterns in the solar convection zone. The current weakness might be a temporary trough, a localized effect of those abnormal polarity regions that could be overcome by later flux emergence. This uncertainty is itself unsettling. We are in a period where the Sun's behavior is diverging from patterns we have come to expect, and our ability to predict what comes next is correspondingly reduced. The polar field reversal for cycle 25 completed in 2023 and 2024, with the northern field changing polarity first in May of 2023, hovering near zero for months, then gradually strengthening through 2024. The southern field reversed in September of 2023. Since then, the northern polar field has been strengthening faster than the southern, which is typical behavior. But now we are seeing signs that this strengthening is about to reverse, at least temporarily in the north. Let me connect this to something we can observe more directly. The polar regions of the Sun are sources of fast solar wind, streams of charged particles that flow outward from coronal holes near the poles at speeds exceeding 700 kilometers per second. During solar minimum, these polar coronal holes are large and stable, dominating the solar wind environment. During solar maximum, they shrink and sometimes disappear entirely as the magnetic field becomes chaotic and the polarity reversal takes place. The strength and configuration of the polar fields influences these coronal holes, which in turn influences the solar wind that bathes our planet. Changes in the polar field geometry can alter the patterns of fast and slow solar wind reaching Earth, affecting geomagnetic conditions in ways that do not require dramatic events like flares or coronal mass ejections. This is the background hum of space weather, the steady-state conditions that power grids and satellite operators plan around. If the northern polar field weakens dramatically in early 2026 as predicted, we may see changes in the coronal hole patterns over the northern solar hemisphere. The fast solar wind streams from the north could become less predictable, their boundaries shifting as the underlying magnetic field evolves. For operational space weather forecasting, this adds another layer of uncertainty to an already complex situation. But there is a deeper mystery here, one that connects to questions about the Sun that we still cannot fully answer. Why do some active regions emerge with abnormal polarity in the first place? The standard dynamo models predict that active regions should follow Hale's law, with leading polarities matching the expected pattern for their hemisphere and cycle. But observations show that a significant minority of regions violate this pattern. These rogue regions are not random errors in an otherwise orderly system. They appear to be fundamental features of solar behavior, emerging from processes in the deep convection zone that we do not yet understand. Some researchers have proposed that abnormal polarity regions arise from magnetic flux that failed to fully reverse during the previous cycle, remnant fields that persist and emerge in opposition to the new cycle's dominant pattern. Others suggest that turbulent convection in the solar interior can flip the orientation of rising flux tubes, producing regions whose polarity is reversed from what the dynamo would predict. Still others point to the role of meridional circulation in transporting and processing magnetic flux, arguing that variations in this flow could produce the observed abnormalities. What is clear is that these abnormal regions have outsized effects on the polar field evolution. A single large rogue region can deposit significant flux of the wrong sign at the poles, partially or even fully cancelling the contributions from many normal regions. The Sun's magnetic memory is surprisingly sensitive to these outliers, these rebels against the prevailing magnetic order. For those who watch the Sun closely, the current polar field evolution is a reminder that our star remains full of surprises. We have been observing the solar cycle systematically since the mid-1700s, when the naming convention for cycles began with Cycle 1 in 1755. We have accumulated centuries of sunspot observations, decades of magnetograph data, and years of high-resolution imaging from space-based observatories. And yet the Sun continues to do things we did not predict, to evolve in ways our models struggle to capture. The exceptionally weak polar field predicted for early 2026 may be a harbinger of a quiet Cycle 26, a multi-year period of reduced solar activity that would have implications for everything from satellite orbital lifetimes to cosmic ray fluxes to possibly even climate. Or it may be a temporary anomaly that the Sun corrects through processes we cannot yet foresee. The honest answer is that we do not know. What we can do is watch, measure, and try to understand. The Solar Orbiter mission that gave us the 94-day observation of the NOAA 13664 is also providing new views of the solar poles from outside the ecliptic plane. Future observations from this and other missions will help us understand the three-dimensional structure of the polar fields in ways that were previously impossible. The data we gather in 2026 may fundamentally reshape our understanding of how the solar dynamo operates. In the meantime, we live with uncertainty. The Sun is entering a critical period, the declining phase of Cycle 25, when polar fields should be building toward the strength that will seed Cycle 26. Instead, we are seeing signs that at least the northern hemisphere is not following the expected script. The quiet before the storm may be quieter than we thought, for reasons we're only beginning to understand, and what that means for the decades ahead remains one of the most important open questions in solar physics. When stars attack, the Carrington ghost and our fragile grid, the questions about Cycle 26 and the strange behaviour of the polar fields take on a different character when we consider what extreme solar activity actually means for our civilization. We have been talking about C-class flares and weak coronal mass ejections, about quiet to unsettled geomagnetic conditions and high-latitude auroras. These are the everyday vocabulary of space weather, the background static of living near an active star. But to truly understand what is at stake, we need to look backward in time to an event that occurred before electricity was woven into the fabric of human society. We need to talk about the Carrington Event. On the morning of September 1st, 1859, an English astronomer named Richard Carrington was doing what he did most clear days. He was observing the sun through his private telescope, projecting its image onto a screen and sketching the dark spots that mottled its surface. What he saw that morning changed history, though he could not have known it at the time. Just before noon, Carrington witnessed something unprecedented. Two patches of intensely bright and white light erupted from a cluster of sunspots, blazing with a brilliance that equaled the direct sunlight itself. The phenomenon lasted only about 5 minutes before fading, but Carrington knew he had seen something extraordinary. He was not alone. Across London, another astronomer named Richard Hodgson was independently observing the same event. The two men would later present their observations side by side to the Royal Astronomical Society, and what they described would become the first recorded observation of a solar flare. But the true consequences of that flare would not become apparent until the following night. The coronals, mass ejection launched by the Carrington flare, travelled the 93 million miles between the Sun and Earth in just 17 hours, a speed that indicates the plasma cloud was moving at roughly 5 million miles per hour. Modern coronal mass ejections typically take 1 to 3 days to reach Earth. The Carrington CME arrived so quickly because it was exceptionally powerful, and because, researchers now believe, a previous eruption may have cleared a path through the ambient solar wind, reducing the resistance the plasma cloud encountered during its journey. When that wall of magnetized plasma slammed into Earth's magnetic field on the evening of September 1st and into September 2nd, the consequences were global and immediate. Aurora borealis, normally confined to high latitudes, blazed across skies as far south as the Caribbean, Colombia, and Hawaii. People in the northeastern United States reported being able to read newspapers by the aurora's light at midnight. Gold. Miners in the Rocky Mountains woke up and began preparing breakfast, convinced that the brilliant red glow on the horizon meant dawn had arrived. In some accounts, the aurora was so intensely red that observers thought nearby towns were on fire, but the visual spectacle was only the beginning. The geomagnetic storm induced by the CME created electric currents in every long conductor on Earth. In 1859, that meant primarily one thing: telegraph wires. Telegraph systems across Europe and North America failed catastrophically. Operators reported receiving severe electric shocks from their equipment. Telegraph paper caught fire in some offices. Sparks showered from the switches and connectors. The induced currents were so powerful that in many locations, operators found they could disconnect their batteries entirely and still send messages, the atmospheric electricity alone sufficient to power the system. A famous exchange between operators in Boston and Portland, Maine, documented in newspapers of the time, described how they conducted a conversation for 2 hours using only the auroral current. One telegraph operator in Washington, D.C., a man named Frederick Royce, was severely shocked when his forehead grazed a ground wire. Witnesses reported that an arc of fire jumped from Royce's head to the telegraphic equipment. He was knocked unconscious. Whether his arm remained paralyzed afterward, as some accounts suggest, cannot be confirmed, but the incident illustrates the very real physical danger that the storm posed to people working with electrical equipment. Now here is the question that keeps space weather scientists and infrastructure planners awake at night. What would happen if a Carrington-class event occurred today? The answer is deeply unsettling. Our civilization has become utterly dependent on technologies that did not exist in 1859. We have wrapped the Earth in a web of electrical conductors that makes the telegraph network look like a child's toy. Power transmission lines stretch for thousands of miles. Undersea fibre optic cables, while not vulnerable to induced currents in the same way copper wires are, depend on electrical repeaters that could be damaged. Pipelines carry sensors and cathodic protection systems that could be disrupted. Railway signalling, as we heard from Louise Harrer discussing the May 2024 storm, depends on electrical systems that geomagnetic storms can affect. And above us, in the fragile shell of near-Earth space, we have placed thousands of satellites that our economy and our military depend upon for communications, navigation, weather forecasting, and countless other functions. A report published by Lloyd's of London in March of 2025 modelled a hypothetical Carrington-class geomagnetic storm striking Earth today. Their scenario involved a coronal mass ejection triggering an hour-long G5 extreme storm, the most severe category on the NOAA, space weather scale. The economic losses they projected ranged from $2.4 trillion over 5 years in a moderate scenario to $9.1 trillion in the most severe projections, and those figures do not fully capture the cascading consequences of widespread infrastructure failure. Consider what happens when the power grid fails. The United States Geological Survey has mapped the geoelectric hazards across the continental United States, identifying regions where geological conditions make the ground particularly conductive and therefore vulnerable to induced currents during geomagnetic storms. The upper Midwest and parts of the East Coast are especially at risk. High voltage transformers in these regions could be damaged or destroyed by the surges of geomagnetically induced current that a major storm would produce. These transformers are not commodity items. They are massive, custom-built pieces of equipment that can take months or years to manufacture and install. A single transformer can weigh hundreds of tons and cost millions of dollars. The United States does not manufacture most of its high-voltage transformers domestically. They come from specialized factories in Europe and Asia. In a scenario where multiple transformers fail simultaneously across a wide region, the wait time for replacements could extend to years. Now imagine what a years-long regional blackout would mean. No electricity means no water pumping stations, which means no clean water, no refrigeration, which means no preserved food, no electronic communications, no banking, no hospital equipment except what can run on emergency generators until the fuel runs out. The USGS does not use the word apocalypse in their technical reports, but the implications are not far from that territory. This is not fear-mongering. This is sober analysis by government scientists and insurance industry experts who have studied the problem carefully. The May 2024 storm, the G5 event that caused spectacular auroras and disrupted GPS for farmers, was significant but not extreme by historical standards. The Carrington event was likely at least twice as powerful, perhaps more. And ice core evidence suggests that events even larger than Carrington have occurred in Earth's past, including a massive solar proton event around 774 AD that left its signature in the radiocarbon content of tree rings worldwide. This 774 event, sometimes called a Miyake event after the Japanese researcher who discovered its signature, was perhaps 20 times more powerful than the Carrington storm. We have no written records of its effects because the civilizations of that era did not depend on electrical technology. But if a Miyake-class event struck today, the consequences would be catastrophic beyond anything in our planning scenarios. Satellites would be destroyed, astronauts in space would receive lethal radiation doses, passengers on high altitude flights could be exposed to dangerous levels of radiation, and the ground-level effects would make the Carrington event look like a minor inconvenience. How often do these events occur? The evidence suggests that Carrington-class storms happen perhaps once or twice per century. A study from 2019 estimated the probability of Earth being hit by such an event between 2018 and 2027 at between 0.46% and 1.88%. Those seem like small numbers until you consider that the consequences of being on the wrong side of that probability are measured in trillions of dollars and potentially millions of lives. We had a near miss in July of 2012. A Carrington-class coronal mass ejection erupted from the Sun and passed through Earth's orbit. Had it occurred just 9 days earlier, when Earth was in that position in its orbit around the Sun, we would have experienced the full impact. Instead, the plasma cloud sailed harmlessly through empty space, and most of the world never knew how close we had come. The current declining phase of solar cycle 25 does not eliminate this risk. As we discussed earlier, some of the most extreme solar events in recorded history have occurred years after solar maximum during the declining phase when overall activity is reduced, but isolated powerful eruptions remain possible. The Halloween storms of 2003 struck more than 2 years after the cycle 23 maximum. we cannot assume that the relative quiet of early 2026 means the danger has passed. What can be done? The honest answer is that our infrastructure is more vulnerable than it should be, and retrofitting it for resilience is expensive and slow. Some progress has been made. NOAA's Space Weather Prediction Center provides forecasts and warnings that allow operators to take protective measures when storms are imminent. Satellite operators can put spacecraft into safe mode. Power grid operators can reduce loads and take transformers offline. These measures help, but they depend on warning time that geomagnetic storms do not always provide. The Carrington Event arrived just 17 hours after the flare. For a similarly fast-moving CME today, we might have only a day's warning, perhaps less. And if the storm arrives during a period when resources are already stressed, when operators are managing other emergencies, when the complex dance of load balancing and protective switching goes wrong, the consequences could be severe. We live in the extended atmosphere of an active star. That is a fact we cannot change. What we can change is how prepared we are for the moments when that star reminds us of its power. The Carrington Event was not a unique occurrence. It was a demonstration of what our Sun is capable of, a preview of a performance that will be repeated. The only questions are when and whether we will be ready. The earthquake, whisper, solar heat, and the crust beneath our feet. There is another connection between our Sun and our planet that remains controversial among scientists, debated in academic journals and dismissed by some as pseudoscience. But recent research has given this connection new credibility, and given what we have been discussing about solar activity, it is worth exploring even if the conclusions remain uncertain. Some scientists now believe that the Sun may influence earthquakes. I want to be clear about something before we go further. This is not established science. The United States Geological Survey, the authoritative voice on earthquake science in America, states explicitly that there is no demonstrated causal relationship between space weather and earthquakes. They note that over the course of the Sun's 11-year variable cycle, flares and magnetic storms wax and wane, but earthquakes occur without any such 11-year variability. This is the mainstream scientific position, and it deserves respect. And yet, in March of 2025, just a few months before I am speaking to you now, researchers from the University of Tsukuba and the National Institute of Advanced Industrial Science and Technology in Japan published findings that suggest the story may be more complicated than the conventional wisdom allows. Their work, building on a 2022 study that found correlations between sunspot activity and seismic patterns, investigated whether Earth's climate, particularly temperature changes driven by solar heat, affects earthquake activity. What they found was intriguing. When they included Earth's surface temperatures in their models, forecasting accuracy improved, especially for shallow earthquakes. Matheus Henrique Junqueira Saldanha, the lead author, explained the proposed mechanism. Solar heat drives atmospheric temperature changes, which in turn can affect rock properties and underground water movement. Such fluctuations can make rocks more brittle and prone to fracturing. Changes in rainfall and snowmelt can alter the pressure on tectonic plate boundaries. This is not the same as claiming that solar flares directly cause earthquakes. The proposed mechanism is more subtle, operating through intermediate effects on Earth's surface conditions rather than through direct electromagnetic coupling. The Sun warms the atmosphere. The atmosphere affects precipitation patterns. Precipitation affects groundwater. Groundwater affects pressure on fault lines. Fault lines slip when the forces exceed the friction holding them in place. It is a chain of causation that extends over weeks or months, not the immediate trigger that conspiracy theorists sometimes imagine when they see a solar flare and an earthquake occurring on the same day. But if the Japanese research is correct, it suggests that solar activity forecasts could eventually contribute to earthquake prediction, one of the holy grails of geophysics that has eluded scientists for decades. The history of attempts to link the Sun and earthquakes goes back more than a century and a half. In 1853, the Swiss astronomer Rudolf Wolf tried to connect sunspots to seismic activity. Since then, researchers have periodically revisited the question, with mixed results. A 2013 paper in Geophysical Research Letters examined 100 years of sunspot and geomagnetic data and found no evidence of a connection. But other studies, including a 2020 paper in Scientific Reports, have claimed to find statistically significant correlations between solar proton flux and earthquake occurrence. The challenge is that both solar activity and earthquakes are complex phenomena influenced by many factors. Finding a correlation between two time series does not prove causation, and the sheer number of researchers who have looked for solar earthquake connections over the years means that some statistically significant results would be expected by chance alone. But there are theoretical reasons to think a connection might exist. The Sun deposits enormous amounts of energy into Earth's atmosphere during periods of high activity. Solar flares ionize the upper atmosphere, changing its electrical conductivity. Geomagnetic storms induce currents in the Earth's crust, currents that could in principle interact with the piezoelectric properties of quartz-bearing rocks. The reverse piezoelectric effect, where applied electric fields cause mechanical deformation, is well-established physics. Whether the fields induced by geomagnetic storms are strong enough to trigger earthquakes remains an open question. What intrigues me about the recent Japanese research is the focus on heat rather than electromagnetic effects. This is a more plausible mechanism because it operates through known physical processes with established effects on rock behavior. We know that temperature changes affect the brittleness of materials. We know that water, infiltration into fault zones, can reduce friction and trigger slip. We know that the Sun's output varies on multiple timescales, from the 11-year sunspot cycle to longer-term variations associated with grand solar maxima and minima. If these variations affect surface temperatures in ways that propagate down to seismically active depths, then a solar earthquake connection becomes more than speculation. The researchers were careful to note that their findings do not suggest solar activity is the primary driver of earthquakes. Tectonic forces, the slow grinding of continental plates against each other, remain the fundamental cause of seismic activity. What the Sun might provide is a modulating influence, a secondary factor that affects the timing of events that were going to happen anyway. Think of it like this. A fault line might be loaded with stress, ready to slip at any time. Small perturbations in the forces acting on that fault, whether from tides, atmospheric pressure, changes, or perhaps solar-induced thermal effects, could determine whether the slip happens today or next week. This is speculative territory, and I want to acknowledge that clearly. But it connects to something we have been discussing throughout this exploration of solar activity. The Sun's influence on Earth extends far beyond the obvious effects of light and heat. The solar wind shapes our magnetosphere. Geomagnetic storms affect our ionosphere, our power grids, our satellite networks. Solar ultraviolet radiation drives chemical reactions in the upper atmosphere. The 11-year cycle modulates cosmic ray flux reaching Earth's surface. Each of these connections was once unknown, then controversial, then accepted science. The solar earthquake connection may follow the same path, or it may prove to be a statistical artifact. We do not yet know. What we do know is that Japan has particular reason to take earthquake predictions seriously. The 2011 Tohoku earthquake, magnitude 9.0 on the Richter scale, generated a tsunami that killed 18,000 people and triggered the Fukushima nuclear disaster. Any improvement in our ability to forecast seismic activity, even a marginal one, could save lives. The research emerging from Japanese institutions reflects this urgency, and there is another connection worth considering, one that is even more speculative but that I mention because it has captured the imagination of some researchers. Could the same solar variations that might influence earthquakes also affect volcanic activity? The mechanisms would be similar, involving thermal and hydrological effects that propagate into Earth's crust. Volcanoes, like earthquake faults, are systems poised on the edge of instability. Small perturbations can have large effects. This is the realm of what I would call scientific possibility rather than scientific probability. The evidence is not strong enough to make confident claims, but as we watch the Sun go through its current cycle, as we observe the unusual behavior of the polar fields and wonder about the quiet that may precede future storms, these connections remind us that our star's influence touches every aspect of our planet. The ground beneath our feet seems stable, eternal, divorced from the drama playing out 93 million miles away in the solar corona. But that sense of separation may be illusion. The same star whose flares can disrupt our power grids and communications may also, through subtle chains of cause and effect, influence the forces that shape our mountains and trigger our earthquakes. We are more connected to the cosmos than our everyday experience suggests. Whether the solar earthquake connection proves to be real or illusory, the research reminds us of something important. Science is not a collection of facts. It is a process of questioning, testing, and revising our understanding in light of new evidence. The USGS is correct that no causal relationship has been demonstrated, but the researchers in Japan are also correct that correlations exist that deserve investigation. The truth, as usual, probably lies somewhere between confident dismissal and credulous acceptance. In the meantime, the sun continues its cycle, the polar fields evolve in unexpected ways, and somewhere on our planet, stress is building on a fault line that will eventually release. Whether these phenomena are connected or merely coincident, they share a common lesson. We live in a dynamic universe, on a dynamic planet, under a dynamic star. The quiet we experience at any given moment is always temporary. Change is the only constant, and understanding the forces that drive that change is the great work of science. Cycle 25's declining phase. What history teaches us about the danger ahead. As we sit here in early January of 2026, we find ourselves in a peculiar position relative to our star. The official word from NASA and NOAA, announced in October of 2024, is that the Sun has reached solar maximum. The peak of solar cycle 25 occurred in that month, with a smooth sunspot number of approximately 161. By the standards of recent cycles, this was a respectable showing. Cycle 24, the previous cycle, peaked at only 82, making it the weakest in over a century. Cycle 25 has exceeded that, confounding early predictions that it would be similarly subdued. But here is what the announcement of solar maximum can obscure for those who do not study solar physics closely. Solar maximum is not a moment, it is a phase. It is not a cliff that activity falls off of, but a broad plateau that can extend for years. And most importantly, reaching solar maximum does not mean the most dangerous solar events are behind us. If anything, history suggests the opposite. Think about what happens as a solar cycle transitions from maximum to its declining phase. The total number of sunspots decreases. The frequency of solar flares drops. Coronal mass ejections become less common. For casual observers, the sun appears to be calming down, settling into a quieter state as it progresses toward the next minimum. This is the narrative we naturally construct, a story of rising action, climax, and denouement that mirrors countless narratives in human culture. But the sun does not read our narrative conventions, and the data tells a different story. Solar cycle 23 peaked in 2001. The largest flares of that cycle occurred in 2003, 2005, and 2006. The X40 class flare, the most powerful ever recorded, erupted in November of 2003, more than 2 years after solar maximum. The Halloween storms of that year, which damaged transformers in South Africa and caused a blackout in Sweden, struck during the declining phase. The September 2005 flares included an X17 class, event that was among the most powerful ever observed. Solar cycle 24 peaked in 2014. Its most powerful flares occurred in September of 2017, more than 3 years after maximum. An X13 class and an X11 class flare erupted from active region 2673, demonstrating that even a weak cycle could produce significant events well after its peak had passed. Why does this pattern hold? Several factors contribute. During the declining phase, the overall magnetic complexity of the sun decreases, but the active regions that do appear can be exceptionally powerful. The magnetic field from the dying cycle still contains substantial energy, and when that energy releases, it can do so with tremendous force. Additionally, the declining phase is when the polar magnetic fields are rebuilding, creating a global magnetic configuration that may favor certain types of eruptions. The statistics bear this out. The highest AP values, a measure of geomagnetic disturbance, typically occur 2 to 4 years after solar cycle maximum. Coronal holes, the sources of high-speed solar wind streams that can trigger geomagnetic storms without any flare activity at all, become more prominent during the declining phase as the polar magnetic field reorganizes. The combination of occasional powerful eruptions from remaining active regions and persistent high-speed streams from equatorial coronal holes can make the declining phase as geomagnetically active as the maximum itself. This pattern has implications for what we might expect in 2026 and beyond. The smooth sunspot number will likely continue to decrease, following the general trend of a declining cycle. We will see fewer active regions on the solar disk, fewer C-class flares in the daily reports, fewer headlines about space weather. But this apparent calm is statistical. It does not mean that individual events cannot be powerful. It does not mean that the sun has exhausted its capacity for extreme behavior. Consider where we are right now. Active region AR 4325, the beta-gamma complex that dominated our discussion at the beginning of this exploration, represents exactly the kind of isolated, powerful region that the declining phase can produce. With fewer competing active regions on the disk, each individual region can grow larger and more complex without interference. The magnetic flux that would be distributed among many regions during maximum becomes concentrated in the survivors. The forecast for the next few days, as we discussed, includes a slight chance for X-class events. NOAA and the SIDC are not issuing this warning because they expect such events. They are issuing it because the magnetic configuration of the current active regions, particularly AR 4325 and AR 4334, contains the potential for such events. Potential is not prediction. But it is acknowledgement that the declining phase does not equal safety. What does 2026 look like from a space weather perspective? Based on historical patterns and current observations, we can make some educated guesses. First, the total number of sunspots will continue to decrease, following the typical declining phase trajectory. By the end of 2026, we may be seeing sunspot numbers in the range of 100 or below, compared to the peak values above 160. This means fewer active regions on average, less total flare activity, and generally quieter conditions. Second, despite this overall quieting, individual active regions can and will produce significant events. The declining phase of strong cycles has historically produced some of the most powerful flares ever recorded. Cycle 25, while not as strong as cycles 21 through 23, exceeded expectations and may yet produce extreme events during its decline. Third, coronal holes will become increasingly important as sources of geomagnetic disturbance. These regions of open magnetic field, which appear dark in extreme ultraviolet images of the sun, can persist for multiple solar rotations, sending recurring streams of high-speed solar wind toward Earth approximately every 27 days. These streams produce moderate geomagnetic storms that can affect satellites, power grids, and high-frequency radio communications even without any flare activity. Fourth, the polar field evolution we discussed earlier will continue to develop in ways that may affect space weather conditions. If the northern polar field weakens significantly in early 2026 as predicted, the geometry of the solar wind may change in ways that are difficult to forecast. The interaction between polar coronal holes and the solar wind could become less predictable. Fifth, and perhaps most importantly, the declining phase is when we need to be most vigilant about extreme events, precisely because they are unexpected. During solar maximum, everyone is watching the sun. Space weather is in the news. Operators are alert to the possibility of storms. During the declining phase, attention drifts to other concerns. The sun seems less threatening. Complacency sets in. The May 2024 storm caught many people by surprise despite occurring during solar maximum. Imagine a similar event occurring in 2027 or 2028, years into the declining phase, when the sun has been relatively quiet for an extended period. The psychological impact of such a storm would be amplified by its unexpectedness. Systems that were carefully monitored during maximum might be receiving less attention. Backup protocols might have become lax. This is not a prediction that such an event will occur. It is an observation that the conditions for such an event will continue to exist throughout the declining phase, and even into the minimum. The sun does not care about our attention or our preparations. It simply accumulates magnetic stress and releases it according to the physics of magnetohydrodynamics. What can we do with this knowledge? For those of us who are not power grid operators or satellite controllers, the practical implications are limited. We cannot personally prepare for a Carrington-class event in any meaningful way. The infrastructure we depend on is either resilient to such events or it is not, and that determination happens at levels far above individual choice. But we can pay attention. we can understand that the declining phase is not the end of the story, but a new chapter with its own characteristics and dangers. We can appreciate that the 7 active regions currently on the solar disk, the C-class flares popping off every few hours, the coronal mass ejection that brushed past us on New Year's Day, are all expressions of a process that continues regardless of where we are in the cycle. The sun burned for 4.5 billion years before humans evolved to observe it. It will burn for 5 billion more after we're gone. Our solar cycles, our sunspot numbers, our forecasts and predictions are human constructs overlaid on stellar processes that operate on timescales we can barely comprehend. In that context, the distinction between maximum and declining phase becomes almost quaint. What matters is that we are here, now, in the extended atmosphere of an active star, and that star will continue to remind us of its presence in ways both beautiful and dangerous for as long as we last. The Terminator Prophecy. How solar tsunamis reset our star. There is a concept in solar physics that sounds like it belongs in a science fiction movie, and yet it may be one of the most important discoveries about our star in recent decades. Scientists call them terminator events, and they appear to mark the precise moment when one solar cycle truly ends and the next begins. Understanding terminators could revolutionize our ability to predict solar activity, and the implications extend far beyond the sun itself to weather patterns here on Earth. The traditional way of defining solar cycles relies on sunspot counts. We identify solar minimum as the point when the smoothed sunspot number reaches its lowest value, and solar maximum as the point when it peaks. Cycle 25, by this definition, began in December of 2019 and reached its maximum in October of 2024. Simple enough. But this approach, while useful for historical record-keeping, obscures something fundamental about how the sun actually works. Scott McIntosh of the National Center for Atmospheric Research and Robert Lehman of the University of Maryland, Baltimore County have spent years studying what they call the extended solar cycle, a 22-year magnetic cycle that underlies the 11-year sunspot cycle we observe. Their research, published in a series of papers beginning in 2014, suggests that solar cycles do not simply fade into one, another at minimum. Instead, they end with a distinct event, a terminator, that triggers the rapid onset of the next cycle. To understand what a terminator is, we need to think about the sun's magnetic field in a different way. Imagine the sun as having bands of magnetic activity in each hemisphere, bands that form at high latitudes and slowly migrate toward the equator over the course of about 2 decades. These bands are associated with the production of sunspots. When the bands from the northern and southern hemispheres finally meet at the solar equator, they annihilate each other, their oppositely signed magnetic fields cancelling out. This annihilation is the terminator. What happens at a terminator is remarkable. The old cycle's magnetic bands disappear almost instantaneously in solar terms, within a single solar rotation, or even less. And immediately, explosively, the new cycle's activity surges. It is as if the sun has been holding its breath, waiting for the old cycle to get out of the way and then exhales in a burst of renewed activity. The researchers describe this as a solar tsunami, a wave of activity that propagates from the equator toward the poles at speeds of around 300 meters per second. The terminator for cycle 24, which marked the true beginning of cycle 25, occurred in December of 2021. McIntosh and Lehman had predicted this timing based on their analysis of extended cycle patterns, and they used it to make a bold forecast. They predicted that cycle 25 would be significantly stronger than the official NASA NOAA prediction of a weak cycle similar to cycle 24. Based on the spacing of terminator events, they forecast a peak sunspot number of around 185, with maximum occurring in July of 2024. The official prediction panel had forecast a peak of 115 in July of 2025. The actual peak, as we now know, was approximately 161 in October of 2024. McIntosh and Lehman's prediction was not perfect, but it was considerably closer to reality than the official forecast. The timing was within a few months, and the amplitude was in the right ballpark. The Terminator framework had proven its predictive value. Why does the spacing of terminators matter for cycle strength? The researchers found a compelling correlation in historical data going back 270 years. The shorter the time between terminators, The stronger the following cycle, the longer the gap, the weaker the cycle. This makes physical sense if you think about it. A longer gap means the old cycle's magnetic bands are lingering at low latitudes for an extended period, interfering with the development of the new cycle's bands at mid-latitudes. A shorter gap means a cleaner handoff, allowing the new cycle to ramp up more quickly and reach a higher peak. The implications of this extend beyond academic interest in solar physics. If terminators are real, predictable events, and if their timing correlates with cycle strength, then we may have a new tool for long-range space weather forecasting. Currently, predictions for upcoming solar cycles are notoriously uncertain. The official prediction panels hedge their forecasts with wide error bars because the underlying physics of the solar dynamo remains poorly understood. Terminators offer a potential shortcut, an empirical relationship that could improve predictions even without a complete theoretical understanding. But the Terminator story gets even more interesting when we consider its possible connections to Earth's climate. Lemon and his colleagues have published research suggesting that Terminator events correlate with La Niña weather patterns in the Pacific Ocean. La Niña, characterized by cooler than average sea surface temperatures in the central and eastern Pacific, affects weather patterns worldwide. It influences hurricane activity in the Atlantic, drought conditions in the American Southwest, and rainfall patterns across multiple continents. The proposed mechanism involves cosmic rays. During solar minimum, when the sun's magnetic field is weak, more galactic cosmic rays penetrate into the inner solar system and reach Earth's atmosphere. These cosmic rays may influence cloud formation through ionization processes, affecting Earth's energy balance. At a terminator, the sudden increase in solar activity strengthens the interplanetary magnetic field, reducing cosmic ray flux. This change could trigger shifts in atmospheric circulation patterns that manifest as La Niña conditions. This is speculative science, and I want to be clear about that. The cosmic ray cloud connection remains controversial, with some researchers finding evidence for it and others finding none. The Terminator-La Niña correlation, while intriguing, is based on a limited number of events and could be coincidental, but if it holds up, it would represent a remarkable discovery, a link between events in the solar interior and weather patterns that affect billions of people. The last Terminator occurred in December of 2021. According to the pattern, La Niña conditions should have followed, and indeed they did. The 2020 to 2023 La Niña was one of the longest on record, a triple dip event that persisted for 3 consecutive years. Correlation is not causation, but the timing is suggestive. When will the next Terminator occur? Based on the current trajectory of cycle 25, we might expect it sometime around 2030 or 2031, give or take a year or two. The polar field evolution we discussed earlier will influence this timing. If the polar fields remain weak, the cycle might extend, pushing the Terminator later. If they strengthen rapidly, the cycle might end sooner. The prediction of cycle 26's strength will depend critically on when this Terminator occurs. A Terminator in 2029 would suggest a stronger cycle 26. A Terminator in 2032 would suggest a weaker one. The researchers are watching the evolution of the extended cycle bands, tracking their migration toward the equator, waiting for the signs that annihilation is approaching. There is something philosophically satisfying about the Terminator concept. It suggests that the apparent chaos of solar activity, the random seeming eruption of sunspots and flares, follows a deeper order. The sun is not simply sputtering through its cycles without pattern. It is executing a complex choreography of magnetic field evolution, with terminators marking the transitions between movements. Each cycle is not independent but connected to its predecessors and successors through the continuous migration of magnetic bands. This deeper order, if it exists, offers hope for improved prediction. The official forecasting methods rely heavily on precursors measured at solar minimum, particularly the strength of the polar magnetic field. These precursors have predictive value, but they capture only part of the picture. Terminators add another dimension, another observable that correlates with cycle behavior. By combining multiple precursors, including terminator timing, polar field strength and other indicators, future prediction panels may achieve greater accuracy. For now, we wait and watch. The sun continues its descent from the cycle 25 maximum, shedding sunspots month by month, gradually approaching the next minimum. Somewhere in each hemisphere, The magnetic bands of Cycle 25 are migrating equatorward, carrying with them the memory of the flares and storms they produced. Eventually, in a few years, they will meet at the equator and annihilate. The Terminator will mark the end of an era and the beginning of a new one. What that new era will bring, whether Cycle 26 will be strong or weak, active or subdued, we cannot yet say with confidence. But the Terminator framework gives us a way to refine our expectations as the critical moment approaches. And in a field where predictions have often been wildly wrong, any improvement in our forecasting ability is welcome. The sun, it turns out, may be more predictable than we thought. Not in the details of when individual flares will erupt or where specific sunspots will form, but in the larger patterns that govern cycle-to-cycle variation. The Terminator is not just an ending. It is a signal, a reset, a promise that the sun's magnetic engine is still running and will continue to drive solar activity for billions of years to come. Digital agriculture under siege, the hidden casualties of space weather. When we talk about the effects of solar storms, the images that come to mind are often dramatic. Power grids failing, satellites tumbling out of orbit, aurora dancing across skies where they have never been seen before. These are the headline-grabbing consequences, the ones that make news and inspire documentaries. But there is a quieter casualty of space weather, one that affects the people who feed us, and it deserves more attention than it typically receives. Modern agriculture has become utterly dependent on precision technology. The tractors that plant and harvest crops on commercial farms are not simply mechanical implements guided by human hands. They are sophisticated robotic platforms guided by GPS signals from satellites orbiting 20,000 kilometers above the Earth. These machines can plant seeds with centimeter-level accuracy, ensuring optimal spacing for crop yield. They can apply fertilizers and pesticides with precision that minimizes waste and environmental impact. They can harvest fields in patterns optimized by artificial intelligence, analyzing satellite imagery of crop health. All of this depends on the same satellite signals that space weather can disrupt. During the May 2024 storm, the G5 extreme event triggered by active region NOAA 13664, modern digital agriculture was particularly affected. The statement comes from Louise Hara of ETH Zurich, one of the researchers who led the 94-day study of that active region. Signals from satellites, drones, and sensors were disturbed, causing farmers to lose working days and leading to crop failures with considerable economic losses. Think about what that means. Farmers have planting windows, narrow periods when soil conditions, weather, and crop biology align to allow successful planting. These windows can be measured in days. If a geomagnetic storm disrupts GPS during a critical planting window, the consequences are not just inconvenience. They are lost crops, reduced yields, economic damage that ripples through the food system. The precision that modern agriculture depends on requires GPS accuracy measured in centimeters. Standard GPS, the kind your phone uses to navigate, is accurate to within a few meters. That is fine for driving to a new restaurant, but useless for planting corn in optimal rows. Agricultural GPS uses correction signals, either from ground-based reference stations or from additional satellites, to achieve the centimeter-level accuracy that modern farming requires. These correction systems are particularly vulnerable to ionospheric disturbances. During a geomagnetic storm, the ionosphere becomes turbulent, filled with irregular structures that scatter and delay GPS signals. The correction algorithms that normally compensate for ionospheric effects cannot keep up with rapidly changing conditions. Accuracy degrades from centimeters to meters, rendering precision agriculture impossible. The May 2024 storm was rated G5, the highest category on the NOAA scale, but agricultural GPS disruption can occur at much lower levels. G3 storms, which are classified as strong rather than extreme, can cause positioning errors that exceed agricultural tolerances. G2 moderate storms can affect the most sensitive operations. During the declining phase of solar cycle 25, we can expect multiple G2 and G3 events per year, each one potentially disrupting farming operations somewhere in the world. The geographic distribution of these effects is not uniform. The ionospheric disturbances that degrade GPS are most intense at high latitudes and in the auroral zones. Farmers in Canada, Scandinavia, and Russia are more vulnerable than those in tropical regions. but major geomagnetic storms can expand the affected zone far toward the equator. During the May 2024 event, GPS disruptions were reported across the continental United States, affecting agricultural operations thousands of miles from the auroral oval. There is also a timing problem that makes agricultural vulnerability particularly acute. The planting and harvesting seasons in the Northern Hemisphere, where most of the world's temperate agriculture occurs, coincide with periods when geomagnetic activity tends to be elevated. Spring and fall, the so-called Russell-McFerran effect predicts, are seasons when the orientation of Earth's magnetic field, relative to the interplanetary magnetic field, is most favourable for geomagnetic storms. The same cosmic geometry that produces aurora seasons also produces agricultural disruption seasons. The economic stakes are significant. Global food production depends on industrial-scale agriculture that has optimized efficiency through technology. The efficiency gains from precision agriculture are measured in percentages, but those percentages applied to global food production translate to billions of dollars and millions of metric tons of food. A 5% reduction in efficiency across global grain production would be catastrophic. Space weather will not cause that kind of systemic reduction, but it can cause localized failures during critical periods that contribute to price volatility and food insecurity. Farmers and agricultural technology companies are beginning to recognize space weather as an operational risk that requires management. Some precision agriculture systems now incorporate space weather forecasts, warning operators when conditions may be unfavorable for high-accuracy operations. Others are developing redundant positioning systems that combine GPS with other satellite navigation constellations like Europe's Galileo, Russia's GLONASS, and China's Beidou. Multi-frequency receivers that can partially compensate for ionospheric effects are becoming more common, but these adaptations come with costs, and not all farmers can afford the most resilient systems. Small-scale farmers in developing countries who are adopting precision agriculture to improve yields and compete in global markets may be using single-frequency receivers without space weather awareness features. They are more vulnerable to disruption and less able to absorb the economic consequences. There is also the question of autonomous agricultural equipment. The industry is moving rapidly toward fully autonomous tractors and harvesters that operate without human drivers. These machines depend even more heavily on reliable positioning because there is no human to notice when something goes wrong and take corrective action. A GPS disruption that causes an autonomous tractor to plant seeds in the wrong location could damage an entire field before anyone realizes the problem. The trend toward automation in agriculture mirrors trends in other industries that space weather affects. Autonomous vehicles on roads will face similar positioning challenges. Drone delivery services depend on GPS. Maritime shipping uses satellite navigation for precise routing. Aviation, both commercial and the emerging sector of urban air mobility, cannot function without reliable satellite services. Each of these industries is building infrastructure that assumes satellite availability and accuracy, assumptions that space weather periodically violates. What I find striking about the agricultural case is how invisible the consequences are to most people. When a power grid fails due to a geomagnetic storm, millions of people experience the blackout directly. When a farmer loses a planting window due to GPS disruption, the consequence is a modest increase in food prices months later that no one attributes to space weather. The connection between a coronal mass ejection and the price of bread is real, but attenuated through so many intermediate steps that it disappears from public awareness. This invisibility is a problem for policy. Investments in space weather forecasting and resilience compete for resources with more visible priorities. Politicians can point to bridges and schools and roads as tangible accomplishments. Pointing to improved geomagnetic storm predictions does not win elections. Yet the economic case for such investments is strong. The losses from a single Carrington-class event could dwarf the cost of decades of space weather research and infrastructure hardening. The farmers who lost working days in May of 2024 understand this in a way that policymakers may not. They experience directly the vulnerability of systems they depend on. They know that the sun is not just a source of light and warmth, but also, occasionally, a source of disruption and loss. As we move through the declining phase of Cycle 25 and beyond, they will continue to watch the space weather forecasts alongside the traditional weather forecasts, hoping that the next storm waits until the crops are in. The sun, of course, is indifferent to agricultural calendars. Active regions form according to the physics of magnetic flux emergence, not the needs of farmers. Coronal mass ejections erupt when magnetic configurations become unstable, regardless of whether it is planting season. This indifference is perhaps the most important thing to understand about space weather. It is not a risk that can be negotiated with or wished away. It is a feature of living near an active star, as fundamental as weather and seasons and the passage of time. The only choice we have is how well we prepare. The weak polar field, paradox, implications for cycle. 26 and beyond. We have touched on the polar field anomaly earlier in our exploration, but now I want to delve deeper into what the current observations might mean for the future of solar activity. The predictions published in December of 2025 by Ruihui Wang and colleagues represent more than an academic exercise. They are a window into the possible futures of our star, futures that could shape space weather for decades to come. Let me state the core finding again because it is that important. The mean polar field of solar cycle 25 is the weakest at a comparable phase. Across the last 5 solar cycles, the northern polar field is predicted to decline sharply until March of 2026, driven by active regions with abnormal polarity. By that time, the northern polar field becomes exceptionally weak, and the southern field remains relatively weak. To understand why this matters, we need to revisit the solar dynamo, the engine that drives the 11-year cycle of solar activity. The sun's magnetic field is generated by the motion of electrically conducting plasma in its convection zone, the outer third of the solar interior where energy is transported by churning currents of hot gas rising and cool gas sinking. This convective motion, combined with the sun's differential rotation, stretches and twists magnetic field lines, amplifying them and organizing them into the patterns we observe as sunspots and active regions. The polar fields play a crucial role in this dynamo process. At solar minimum, the polar fields represent the seed from which the next cycle grows. The meridional circulation, a slow poleward flow at the solar surface and an equatorward return flow at depth, transports this polar flux into the convection zone where it is processed by the dynamo. Stronger polar fields at minimum tend to produce stronger subsequent cycles. Weaker polar fields tend to produce weaker cycles. This relationship has been observed across multiple solar cycles and is the basis for the precursor methods that prediction panels use to forecast future activity. The strength of the polar field at minimum is the single best predictor we have for the amplitude of the upcoming cycle. It is not perfect. Correlation is not destiny, but it is the most reliable tool in our predictive toolkit. What the December 2025 study tells us is that the polar fields of cycle 25, still more than 3 years from the expected minimum, are already unusually weak. If this weakness persists through the minimum, it suggests that cycle 26 may be subdued, possibly weaker than cycle 25, possibly approaching the quiet conditions of the early 20th century. But there is a paradox here that the researchers themselves acknowledge. Polar fields can strengthen rapidly during the declining phase. The flux from active regions takes time to be transported to the poles, several years for the meridional circulation to carry it from the active latitudes near the equator to the polar regions. Active regions that emerge in 2026 and 2027 could contribute flux that arrives at the poles in time to strengthen the field before the cycle 25-26 minimum. The current weakness is driven in part by abnormal polarity regions, active regions whose magnetic orientation violates the expected pattern for their hemisphere. These rogue regions deposit flux of the wrong sign at the poles, partially cancelling the contributions from normal regions. If the rate of abnormal region emergence decreases in the coming years, the polar fields could recover. This uncertainty is frustrating for anyone seeking clear predictions, but it reflects the genuine complexity of solar dynamics. The sun is not a simple system with easily predictable behavior. It is a turbulent magneto-hydrodynamic engine with chaotic elements that can amplify small differences into large variations in outcome. The difference between a strong cycle 26 and a weak one might depend on the emergence of a handful of active regions with particular magnetic configurations, events that cannot be predicted years in advance. Let me explore what the different scenarios might mean for space weather and for those of us who live under the sun's influence. Scenario 1 is a weak cycle 26, comparable to or weaker than cycle 24. This would mean reduced solar activity through the early to mid-2030s, fewer sunspots, fewer flares, fewer geomagnetic storms. Satellite operators would benefit from reduced atmospheric drag in low Earth orbit. Power grid operators would face fewer threats from geomagnetically induced currents. Aurora would retreat to the highest latitudes, rarely visible from populated regions. But a weak cycle does not mean no extreme events. As we discussed earlier, some of the most powerful individual flares and storms have occurred during weak cycles or their declining phases. A quiet sun can still produce isolated, powerful eruptions that catch an unprepared civilization off guard. And the reduced overall activity might breed complacency, making such events more damaging when they occur. Scenario 2 is a moderate cycle 26, similar to cycle 25. This would represent a continuation of current conditions, with regular space weather events but no dramatic intensification or reduction. The infrastructure and operational procedures developed during cycle 25 would remain appropriate, requiring only incremental updates. Scenario 3 is a stronger cycle 26, perhaps approaching the levels of cycle 23 in the late 1990s and early 2000s. This would mean increased solar activity through the 2030s, more frequent and more powerful storms, greater threats to technological infrastructure. Such a scenario seems less likely given current polar field observations, but it cannot be ruled out. The Sun has surprised forecasters before and will do so again. Beyond these near-term scenarios, there are longer-term questions about where we are in the grand cycles of solar activity. Some researchers have proposed that solar activity exhibits century-scale variations, with periods of enhanced activity like the modern maximum of the late 20th century alternating with periods of reduced activity. If we are entering a period of reduced activity, the weak cycle 25 polar fields might be early indicators of a multi-decade trend toward quieter conditions. The most extreme version of this scenario invokes the Maunder minimum, a period from approximately 1645 to 1715 when sunspots became extremely rare. During the Maunder minimum, the normal 11-year cycle essentially disappeared, with decades passing without significant solar activity. This period coincided with the coldest phase of the Little Ice Age in Europe, though the causal connection between solar activity and climate remains debated. Are we heading toward another Maunder minimum? Most researchers consider this unlikely. The current polar field weakness, while notable, is not unprecedented when viewed across the longer historical record. Solar activity has varied substantially over the centuries without triggering extended grand minima. The factors that cause the Sun to enter Maunder-like states are not well understood, but they appear to involve processes operating on timescales longer than a single cycle. Still, the possibility cannot be entirely dismissed. The Sun is a complex system with behaviors that emerge from the interaction of multiple processes operating on different timescales. We have only been observing the Sun with modern instrumentation for a few decades, a tiny fraction of its history. Our understanding of its long-term variability is necessarily limited. What seems most likely, based on current evidence, is that cycle 26 will be moderate to weak, continuing the general pattern of reduced activity that has characterized the past several decades compared to the mid-20th century. This is not a dramatic prediction, but it is a useful one for planning purposes. Infrastructure designed to withstand cycle 25 conditions will probably be adequate for cycle 26. But this planning should not assume that extreme events are impossible, only that they may be somewhat less frequent. The polar field observations coming from solar orbiter and ground-based magnetographs over the next few years will refine these expectations. As we approach the cycle 25 minimum, the polar field strength will become increasingly diagnostic of what cycle 26 will bring. By 2028 or 2029, we should have a much clearer picture of the road ahead. In the meantime, we live with uncertainty, as humans always have when contemplating the behavior of forces beyond our control. The Sun will do what it does, according to the physics of magnetohydrodynamics and the contingencies of its internal dynamics. We can watch, measure, predict within limits, and prepare for the range of possibilities. That is the best any civilization can do when living in the extended atmosphere of an active star. Living with our volatile star, preparation for the inevitable. We have journeyed through the current state of solar activity, from the 7 active regions dotting the Sun's face today to the 94-day revelation of how superactive regions develop and decay. We have explored the strange behavior of the polar fields and what it might mean for cycles to come. We have confronted the ghost of the Carrington Event and the very real threats that extreme space weather poses to our technological civilization. We have considered the subtle ways the sun might influence earthquakes and the not-so-subtle ways it disrupts modern agriculture. We have learned about terminators and solar tsunamis, about the declining phase paradox and the weak polar field enigma. Now, as we near the end of our exploration, I want to ask a simple question. What do we do with all of this knowledge? The honest answer is that for most of us, the practical implications are limited. We cannot personally harden the power grid against geomagnetically induced currents. We cannot redesign GPS satellites to better resist ionospheric disturbances. We cannot influence the policies that determine how much society invests in space weather forecasting and infrastructure resilience. These are decisions made at institutional levels by governments and corporations and international bodies, decisions that reflect priorities shaped by countless factors beyond individual control. But there is value in understanding even things we cannot directly affect. Knowledge changes how we see the world, and how we see the world changes how we move through it. Consider what it means to truly understand that we live in the extended atmosphere of an active star. The sun is not just a yellow disk that rises and sets, a source of light and warmth and sunburns. It is a nuclear furnace 500 times more massive than all the planets combined, churning with magnetic fields that store and release energy on scales that dwarf anything in human experience. The quiet sunrise you witnessed this morning was the light from a star that could, at any moment, launch a plasma cloud capable of disrupting civilization. This is not cause for fear, it is cause for awe and perhaps for humility. Humanity has achieved remarkable things. We have built global communications networks and power grids and satellite constellations. We have connected billions of people through technology that would seem magical to our ancestors. But all of this exists within constraints set by our cosmic environment, constraints we did not choose and cannot escape. The space weather community has been working for decades to improve our understanding and our preparedness. NOAA's Space Weather Prediction Center issues forecasts and warnings that allow operators to take protective measures. NASA and ESA and space agencies around the world operate spacecraft that monitor the sun continuously, providing the data that feeds into these forecasts. International collaborations share information across borders because space weather does not respect national boundaries. Progress is being made. The Solar Orbiter mission that gave us the 94-day observation of NOAA 13664 represents a leap forward in our ability to monitor solar activity. Future missions, including spacecraft that will observe the sun from multiple vantage points simultaneously, will further improve our situational awareness. Machine learning systems are being developed to analyze solar data and identify patterns that human forecasters might miss. The science of space weather prediction is advancing year by year, publication by publication, observation by observation. But progress is not the same as solution. We are still far from being able to predict exactly when and where the sun will produce dangerous eruptions. We cannot forecast with confidence whether a particular active region will produce an X-class flare or fade quietly into obscurity. We cannot predict, except in statistical terms, when the next Carrington-class event will occur. And even if we could predict such an event with perfect accuracy, our ability to protect our infrastructure on short notice remains limited. This is the situation we find ourselves in, dependent on technologies that space weather can disrupt, aware of the threat, but unable to eliminate it. Making incremental progress in prediction and resilience, but still far from where we need to be. What can individuals do? We can stay informed. Space weather forecasts are publicly available from NOAA and other agencies. During periods of elevated solar activity, checking these forecasts can provide awareness of when aurora might be visible or when communications might be disrupted. For those with specific vulnerabilities, such as people who depend on GPS for their livelihood or who have medical devices sensitive to electromagnetic interference, understanding space weather conditions can inform decisions. We can also advocate for preparedness. Public awareness of space weather risks influences political priorities. When voters understand that the power grid is vulnerable to solar storms and that investments in resilience could prevent catastrophic failures, they can push for those investments. The same is true for space weather research funding, for satellite hardening standards, for emergency planning that accounts for space weather scenarios, and we can appreciate. There is profound beauty in the phenomena we have been discussing. Aurora are the visible signature of the sun's interaction with our planet, curtains of light that have inspired wonder since humans first looked up at the sky. Solar flares and coronal mass ejections, for all their potential destructiveness, are expressions of physics operating on scales we can barely comprehend. The 11-year cycle, the Terminator events, the polar field reversals, these are the rhythms of a star that has burned for 4.5 billion years and will burn for 5 billion more. We are privileged to live in an era when we can understand these phenomena, even as we grapple with their implications. The sun rose this morning over a planet going about its business, 7 billion people living their lives largely unaware of the magnetic complexity seething 93 million miles away. Active region AR 4325 is still there, still firing off C-class flares, still holding the potential for something larger. The polar fields are still evolving in unexpected ways, building or eroding the seed for Cycle 26. The next Terminator event is years away, but the magnetic bands are migrating equatorward, carrying the sun toward its next phase transition. Time will pass, cycles will come and go, some will be remembered for their extreme events, others forgotten in the statistical noise. Eventually, perhaps next year, perhaps in a decade, perhaps in a century, a coronal mass ejection will hit Earth at just the wrong angle, with just the wrong magnetic configuration, at just the wrong time. The aurora will dance across unprecedented latitudes. Power grids will strain or fail, satellites will tumble, and humanity will be reminded, as it is reminded periodically throughout history, that we are small creatures living in the shadow of forces vastly greater than ourselves. That reminder is not cause for despair, it is cause for perspective. We have built remarkable things. We will build more. We will adapt to the challenges the sun presents, as we have adapted to every other challenge the universe has thrown at us. The story of humanity is a story of resilience, of finding ways to thrive in environments that often seem hostile to our survival. But resilience requires awareness. It requires understanding the risks we face and making choices that account for those risks. It requires humility about what we can control and determination to control what we can. In the case of space weather, that means continued investment in science and forecasting, in infrastructure resilience, in international cooperation. It means taking the threat seriously even when the sun is quiet, even when the last major storm fades from memory, even when other priorities compete for attention. The sun will continue its cycles indifferent to our preparations, but we do not have to be indifferent to the sun. We can watch, we can learn, we can prepare, and when the next great storm comes, as it inevitably will, we can face it with the knowledge and the infrastructure and the resilience that our awareness has built. Thank you for joining me on this exploration of our volatile star. If you found value in what we have discussed, I hope you will share it with others who might benefit. The more people understand space weather, the better prepared our civilization will be for the challenges ahead. Like and subscribe if you want more content like this. The algorithm pays attention to those signals, and your engagement helps bring these topics to a wider audience. Leave a comment telling me where you are listening from and what aspect of solar activity most fascinates or concerns you. I read every comment, and your perspectives help shape future explorations. As always, remember that the science we have discussed is our best current understanding, subject to revision, as new observations and analyses become available. The sun is full of surprises, and what we think we know today may be overturned by what we learn tomorrow. That is the nature of science, and it is part of what makes studying the cosmos so endlessly fascinating. Until next time, stay curious, stay aware, and keep watching the skies. The sun is always there, burning steadily, holding its secrets, and occasionally revealing them in spectacular fashion. We are lucky to live in an age when we can understand it, even as we remain humble before its power. Good night, and may your skies be clear and your power grid stable.